We now move into talking about transformations of log of x. Now, this is probably one of the heavier sections in this topic because we're going to be bringing together a lot of different ideas and there's I guess a lot of prior work that we just need to refresh our memories of before we get into actually doing work with transforming ln of x. So the first thing that we need to recall is just the types of transformations that we can see. So the first type is a translation. A translation means that we're just shifting the graph around. We're not changing its shape, we're changing its location. So for example, we might have a graph that looks, say on a set of axes, that looks a little bit like this. We're going from that to say that, right? We're not changing the direction at all. We're just moving it horizontally or maybe vertically, or both. For a dilation, this is where we are changing the shape. We're stretching it in some way. We usually talk about stretching it horizontally or vertically, and we stretch it in terms of a scale factor. That scale factor tells us how many times further away from the axis line where we're sort of stretching it from, how much further away from the axis we are. So for example, we might have a set of axes that looks a little bit like this now. We have a graph, okay? If we're stretching it vertically, then we're stretching it around the x-axis. So this point here that's on the x-axis, that's going to stay put, but everything's going to be 3 times as far away, okay? So the further away that the initial point is, we're going to be much further away on the new point, right? Everything is 3 times as far from the x-axis, or 1/3 the distance on the y-axis, or something like that. The final type of transformation is a reflection. This usually occurs through a horizontal or vertical line, and in nearly every single situation, that's actually going to be through the x or y axes. Just be, I guess, mindful of that. Now, we've seen these transformations before. We've seen it in the context of trigonometric functions. So you might have seen that little equation there previously. Just to refresh your memories, each of these parameters does something slightly different. So A tells us the amplitude. Now, the amplitude is a specific term for trigonometric, for periodic functions. In fact, this really is our dilation, a vertical dilation with a scale factor equal to A. Okay, everything is A times as far away from the x-axis as it was if the A wasn't there, right? If we had 3 sine of x, everything is 3 times as far away, right? The maximum is 3 rather than 1, okay? So that's the first term in there, the first parameter. The second parameter, B, tells us the period, right? The period, if a period is of a periodic function, is equal to 2 pi over b. Now, we're talking about logarithms here. Logarithms are not repeating functions. They don't have a period. What they're going to do is they're going to talk about dilation here. This is a horizontal stretch. So this is a horizontal dilation. And we have a scale factor of 1 over b. Okay, notice how the period is 2 pi over b. Like that b is in the denominator. It's the same thing with the horizontal dilation. For C, this is our third parameter. This is now changing, I guess, our horizontal position. We have a horizontal translation. And we're moving C units to the right. Just notice how we do have a negative in here. It is kind of like, B and C kind of do things opposite to what A and D will do. just be mindful of that. So C is a horizontal translation. Finally, D is our vertical translation. And that's going to be D units up. Now, all of these statements, apart from amplitude and period, all of those statements are true for all of any function that looks like this. Okay, so if we, instead of having sine, which we have here, we had just our function of this going on, whether we had like ln here or whether it was all of this to a power or something, we've got the same kind of relationship here. The one thing that we just need to be aware of is A and B will do something else. So we've talked about dilations and translations. We haven't talked about reflections. If A is negative, then we not only have a vertical dilation through a scale factor of A, we've got a reflection through the x-axis. And if B is less than 0, that's a reflection through the y-axis. So let's start to now unpack this in the context of the graph of y is equal to ln of x. When we look at this particular equation here, we've got a few parameters. It looks kind of like what we were just looking at, but there's no d parameter. Ln kind of does a couple of interesting things. Let's have a look at it. Let's actually do some manipulation here using the log laws. So what that means is we can write this as a times ln of b bracket x minus c. We can also write this even further as a ln b plus a ln x minus c. Okay, using the third and then first log laws. What this means is that we could have a number of different things going on, and it can get quite complicated. The first thing that we're going to see here is we've got a horizontal translation, C units right. Then we have a vertical translation, ln B units up. Continuing on, we have a vertical dilation through a scale factor of A. Finally, a vertical reflection through the x-axis if our value for A is negative, or a horizontal reflection through the y-axis if B is negative, through the y-axis, or the line x is equal to c if we've already got a horizontal translation. This order really relates to the order of operations on x. What I would strongly suggest is don't stress about memorizing all of that in the order in which things are going in, because typically it is going to go in this order. But have a look at the equation that you're given. You're not going to get all of A, B, and C all together. So the most that we're really going to do, the most I've ever seen in an exam, is a couple of these parameters. And I think the reason for that is it starts to get quite complicated, and I think that means that it's going to be really sort of difficult to assess. Let's just look at a couple of situations where we can see how that order of transformation does change things. So we've got two really similar looking functions here. ln of 2x to the power of 5 and ln of 2x to the power of 5. Okay. If we start to manipulate these, so let's look at the first one. Right, that's equal to 5 ln 2x, which is equal to 5 ln 2 plus 5 ln x. That means that this here is a transformation. We have got a vertical dilation with a scale factor of 5. Then vertical translation, 5 ln 2 units up. Okay. We can actually also represent this. Let's actually do this a little bit better. This is going to highlight what I'm really talking here about, the similarity of being able to describe these transformations. This one here, we have got a vertical translation, ln 2 units up, followed by a vertical dilation with a scale factor of 5. When we look at the other one, here we've got ln of 2x to the power of 5. We can write this as ln 2 plus 5 ln x. When we describe this to the x, so when we're looking at this part here, we're multiplying it by 5, so this gives us a vertical dilation through a scale factor of 5. Then a vertical translation, ln 2 units up. My point here is, let's actually get the then in there. My point here is, sometimes the order of transformation is going to impact the graph that you're working with. So what you need to do is think about what is happening to the x and what is happening to ln x. Okay? If you have that sort of mind frame, right here, we had ln x, we added ln 2 to that, so it's a vertical translation. Then we multiplied it all by 5, so it's a vertical dilation. So if you're thinking in that sort of way, you're going to have a much easier time describing the transformations that we're looking at. Let's get into some examples here and let's see what we find. So first up, we've got describe the transformation from f of x is equal to ln x to f of x is equal to ln of 2x cubed. Let's do some manipulation here. So we have got 3 ln x, 3 ln of 2x, which is equal to 3 times ln 2 plus ln x. It's really helpful if you can get that ln x isolated. That then means we have got a vertical translation, ln 2 units up, then a vertical dilation of scale factor 3. And that's it. That's how we describe that transformation. Let's look at another one. Here we've got the transformation from ln x to ln of 3x plus 1. Let's try and get this in a form that looks a little bit more like what we're comfortable seeing here. So f of x is equal to ln of 3 times x plus 1/3. Right? If we were to expand that out, we would get 3x plus 3 times 1/3, which is 1. This is really sort of emphasizing, we've got a constant times x plus or minus something. Okay, we don't really like seeing this because you know what's going on over there. All right, that's equal to ln 3 plus ln of x plus 1/3. So that means we've got a horizontal translation. Because it's x plus 1/3, we're shifting towards the left, so 1/3 of a unit left. Then a vertical translation, ln 3 units up. And 2 more examples. Let's just correctly notate these ones. There's C and D. Here we've got ln of x going into ln of 4 minus x. We really want to see it in that form of constant times x plus or minus something. We really don't want to have like a coefficient of just the x in there. So it's kind of similar to the last one. We do need to do some manipulation here. So f of x is equal to ln. Let's write this as the negative of x minus 4. The advantage of doing this is we can see clearly what's b and what's c in this case. Let's work through this. We can't really expand that out, right? We're not going to get ln of negative 1 plus ln of x minus 4. Really what this means is we've got a horizontal translation, 4 units right. And then we've got a reflection. A reflection through this new asymptote line at x is equal to 4. Okay, if we sort of think about it, here's our graph. All right, we start off with ln kind of looking like this. We've shifted everything 4 units across. Okay, it looks kind of like that. But then we're reflecting this. Now we're reflecting it through this line here. So it's going to ultimately look like that. If all else fails, graph this on your graphics calculator. See what it is that you're looking at and make sure that what you're describing in words matches what you're seeing. You don't need to just do this all in your head, right? Use visual clues to help you out. The final option that we have here, we've got ln of negative 1 on x. This is looking really weird, so let's tidy it up. That's equal to the ln of negative x to the power of negative 1, which is equal to negative ln of negative x. This is actually just a reflection through both axes. So we've got a reflection through the x-axis and the y-axis. That's all the examples. I know this one's gone a little bit longer, but there's a little bit more ground to cover here. Have a go at the questions in exercise 2.3. Some of them are very friendly. Some of them require a little bit of work. Some of them are just talking about a single transformation. Some of them will require you to do multiple